So in the last video we discussed how for finite sets A and B that the cardinality of A and B are equal. That's equivalent to saying that there's a bijection between A and B. And that if the cardinality of A is less than or equal to the cardinality of B, then there exists an injection from A to B. And that's an equivalence as well. And if the cardinality of A is greater than or equal to the cardinality of B, then there exists a surjection from A to B, a surjective function. And I'll just note here quickly as a corollary of these three that the cardinality of A is less than the cardinality of B. Well, by 2 that means there exists an injection from A to B, but there can exist a surjection from A to B in this case because if there were a surjection, then by 3 the cardinality of A would have to be greater than or equal to B, which it's not. And similar reasoning leads to 5, that if the cardinality of A is greater than the cardinality of B, then there's a surjection from A to B, but no injection from A to B. So we'll get to talking about all of these points later, but just remember from last time we used 1 here. We sort of flipped this around and used this as a definition of the cardinality of 2 sets being equal for any 2 sets whatsoever, not necessarily being finite. So for example, recall we showed that the cardinality of the natural numbers is the same as the cardinality of the integers. We produced a bijective function from the naturals to the integers. And also the interval of real numbers from 0 to 1 has the same cardinality as the interval of real numbers from 0 to infinity. We also produced a bijective function mapping one to the other in that case. So I want to make a further remark on point 1 as a definition. So for any set A, there's a natural bijective function from A to itself. The identity function on A, which just takes any x to x. Right? So this tells us that the cardinality of A is equal to the cardinality of A for any set A. Right? Secondly, if we have 2 sets A and B such that the cardinality of A equals the cardinality of B, what that means is that there's a bijective function from A to B. And then if we consider the inverse of that function, since it's bijective, it has an inverse, just flip the arrows around, that's going to be a bijective function from B to A. So the cardinality of B equals the cardinality of A. And so we have to be a little bit careful about our definition of bijective, our definition of cardinality of A equals cardinality of B. That means there exists a bijective function from A to B. So it's actually kind of directed. It matters which set is on the left, at least a priori, but this lets us see that it actually doesn't matter because we always have the inverse function to go the other way. And lastly, if the cardinality of A equals the cardinality of B and the cardinality of B equals the cardinality of C, that means there are bijections from A to B, say F, and G from B to C, and then we can compose those bijections and we get a function from A to C. And that's a bijection too, because we showed previously that the composition of injective functions is injective and the composition of surjective functions is surjective. So the composition of bijective functions is bijective. And therefore we have a bijection from A to C, and so the cardinality of A equals the cardinality of C. So all this is to say, of course, that the notion cardinality of A equals cardinality of B is just an equivalence relation, right? So we can define A is related to B if and only if cardinality of A equals cardinality of B, that is, if and only if there's a bijection from A to B, and that's an equivalence relation on sets. Though logically that runs into a little bit of trouble, which we'll kind of just ignore, which is the fact that there's no such thing as a set of all sets. Because Russell's paradox that we discussed earlier in the semester implies that a thing like the set of all sets doesn't make logical sense. So there's no all-encompassing set of sets on which to define this relation. But in some sense, I mean, yeah. But between any 2 sets, or between any 3 sets, the properties A, B, and C are going to hold. So that'll just be useful for us to know going forward. So one interesting thing that we can observe from this fact that that cardinality of A equals cardinality B is sort of equivalent to an equivalence relation is that we can use this to define the cardinality of A as a standalone object. So right now we just say the cardinality of A is the same as the cardinality of B if there's a bijection from A to B. But we can define the notion of the cardinality of A as a thing in its own right. The definition is that the cardinality of A it's essentially like the equivalence class of A with respect to this relation on sets that we have above. So the cardinality of A is just all of the sets for which there's a bijection from that set to A. Right? So it's basically all the sets with the same cardinality as A. And so where that comes from is think about the analogy between this thing here, A related to B, if and only if cardinality A equals our cardinality B, and what we know holds in the theory of equivalence relations, which is that X is related to Y down here. X is related to Y if and only if the equivalence class of X is equal to the equivalence class of Y. And now with this definition of the cardinality of A, one can prove that the cardinality of A equals the cardinality of B. That is, those two sets defined by this definition here are equal if and only if there's a bijection from A to B. And that's just, the proof just uses the properties A, B, and C up here, just the reflexive, symmetric, and transitive properties, just like the proof of this condition of that fact holds for general relations. Now I want to point out that the definition given here for the cardinality of a set becomes very interesting even for finite sets because it gives us a way to a new way to think about natural counting numbers. So say, for example, that in the usual sense of talking about it, the cardinality of a finite set A is equal to n. Now, compare this equality, n equals cardinality of A, to the definition of the cardinality of A above. Right? So the cardinality of A defined above is the set of all sets X, which are in bijection with this particular set A of n elements. Right? So it's the set of all sets which have n elements in the usual sense. So basically this tells us that if you read through this equality, that n we can interpret in its Platonic essence, in a sense. It's the set of all sets that have the same number of things as the particular set A that has n elements in it. And so we're sort of using n in two different senses. So when we think about n as the set, that's like sort of the Platonic essence of what this number n means. It's the quality, the abstract essence that is common to all sets with that same number of elements in it. And so you might imagine you have like 10 ducks and 10 sheep and 10 cows, right? So all of those things sort of embody tenness in the sense that what's mutually common between all of them is that they're in bijective correspondence with each other. It doesn't matter that ducks have feathers and cows have have hair or whatever. All that matters is the quantity that they can be put into bijective correspondence. So that sort of gives you a philosophical way of thinking about what a number really is in some deeper sense. It's this abstract quality that's shared by every particular collection with that number of elements in it. So enough with the overly philosophical remarks. Let's take a look at a practical application of the transitive property of cardinality, of equality of cardinality. So last time, we already know. So one thing we know is that the cardinality of the interval from 0 to 1, that's equal to the cardinality of the interval from 0 to infinity. And so what we're going to show is that the cardinality, so we'll show, is that the cardinality of the interval from 0 to 1, that's equal to the cardinality of all of the real numbers. And it suffices to show, So it suffices by transitivity to show that the cardinality of 0 to infinity is equal to the cardinality of R. Right. So in order to do this, let's take a look at a familiar function. So consider f, which takes the reals to the positive reals, defined by e to the x. Right, so we know this is a bijection. This is a bijection since f inverse exists. F inverse of x is just the logarithm function, or the natural logarithm function, right, which is, of course, defined for all the positive reals. So that tells us, so therefore, the cardinality of R is equal to the cardinality of 0 to infinity. And also, I guess we're going to use the symmetric property too. So the cardinality of 0 to infinity, that's equal to the cardinality of R, right? And that was what we were trying to show, because now, since the cardinality of 0 to infinity is equal to cardinality of R, so you can combine this with this that we already know, and just concatenate those with the transitivity, and then we see that the interval. So indeed, the interval from 0 to 1 has the same cardinality as the interval of all of the real numbers. And since, so you can use linear functions to bijectively correspond 0, 1 to any interval from a to b. So the real numbers have the same cardinality as any subinterval of the real numbers that you're looking at. So now I want to return to where we started. So we have these facts 1 through 5 for finite sets, but what we're going to do now is turn this into a definition for any set, any two sets, A and B. So definition for any sets A and B. We use these as definitions. So cardinality of A equals cardinality of B. That means exactly that there's a bijection, right? As we've seen. If we want to say, so if there exists an injection from A to B, then we say that the cardinality of A is less than or equal to the cardinality of B. That's 2. If there exists a surjection, then the cardinality of A is greater than or equal to the cardinality of B. If there is an injection from A to B but no surjection, then the cardinality of A, we say that's less than the cardinality of B. And if there's a surjection but no injection from A to B, then the cardinality of A is greater than the cardinality of B. Okay, so just like with the bijective and equality of cardinality definitions, we define these other notions of less than or equal to, less than, greater than, equal to, greater than, by using the injection and surjection on the right-hand side as definitions of those concepts. So one way you can think about this is that these symbols, less than or equal to, greater than, equal to, less than, greater than, they become relations between the equivalence classes of the sets described by cardinality of A, right? So remember, cardinality of A we can define as a set, and then all of those sets, you can define these equivalence relations between them using these notions here. The first big surprise when studying cardinality is that there are infinite sets of different size. And so if you take size in the sense of cardinality and you think about these equivalence relations as sort of as less than really meaning in some sense that the set on the left is smaller than the set on the right, there are different sizes of infinity. There are infinities that are smaller than other infinities. And so the first example you usually look at of that is that the natural numbers, so the infinity that's represented by the collection of the natural numbers, is smaller than the infinity that's represented by the collection of the real numbers. So just remember, in terms of the definition, what this means is that there is an injection from the natural numbers to the real numbers. So this is what we're claiming. There's an injection from the natural numbers to the real numbers, but any function from the natural numbers to the real numbers fails to be surjective. There is no surjection from the naturals to the reals. He says this might seem pretty weird. I mean, there's an infinite number of things in the natural numbers. You might think we could cover all of the infinitely many things with that infinitely many things in the real numbers, but that's just not the case. So you might intuitively think of the real numbers is an interval, like every point here, right? But n is just a sort of discrete collection of points. So there's no way, if you try to jam all these points up together to make an interval, you can never do that. So all of those little single points you can never put together and make a full interval. Okay, so you might want to just try to see if you can visualize that in some sense. I know it's a little bit of a stretch of the imagination at first. So here's the proof. So clearly there's an injection. So clearly, if we define f from the naturals to the reals by defined by f of n equals n, right? So you think about your input n is a natural number, but natural numbers sit inside the real numbers. So that's an injection. It's clearly an injection, right? You don't have two different natural numbers going to the same natural number by this map. It's just like the identity map on the natural numbers. Okay, so there is an injection. That's fine. So to show there is no surjection, we will show there is no surjection from G to the from the natural numbers to the interval from 0 to 1. So if we do this, if we do this, there can be no surjection H from the naturals to the reals, because if there were, then composing H with the bijection from R to 0, 1, right? So we know they have the same, R and 0, 1 have the same cardinality, so there's a bijection between them, would give, right? So a bijection is surjective. If we had a surjective map from the naturals to the reals and then follow up with this bijection from the reals to 0, 1, then we would have a surjection from the naturals to 0, 1. But that's the thing that we're going to prove cannot exist. Okay, so there can't be then a surjection from the naturals to the reals. So if there were, then composing H with the bijection from R to 0, 1 would yield a surjection from the naturals to 0, 1. Okay, and that's the thing we are showing does not exist. So let G from the naturals to 0, 1 be any function. So we will show that there is some beta, in this interval 0, 1, which is not in the range, of G. So just remind you what that means, that i.e. beta doesn't equal g of x for all x in the natural numbers. The argument we will give is called Cantor's diagonalization argument, and it's one of the absolute classic arguments in mathematics. So the argument we give is called Cantor's diagonalization argument. Okay, so we have this given function g from the naturals to this interval from 0 to 1. And what we're going to do is we're going to write down a list. So we have g of 1, that's going to be equal to some real number in 0, 1. So it's going to have a decimal expansion, right? So it's going to look like A1, A2, A3, A4, A5, ... right? And then G2 is going to be B1, B2, B3, B4, B5, ... G3. Okay, so I filled in the rest there. And what we're going to take for granted is that any real number has a unique decimal expansion as long as we don't, and the uniqueness part, as long as we don't allow infinite strings of 9s. And so you might be aware of the fact that, something like 3 and then 9, 9, 9, right? The 9 repeating is the same thing as 0.4. Right, so that would look like two different decimal representations of the same thing. So as long as we always replace infinite strings of 9s by an equivalent decimal representation, then we have uniqueness of the decimal expansion. Okay, and so the basic idea of the argument is that we're going to just write down some real number in the interval 0 to 1, which is not any of the ones on this list given here. And the basic idea is actually relatively simple. All you do is you look at the first digit of the first number, and your first digit of the number that we're going to write down we're going to claim is not in the image is going to differ from that first digit of the first one, right? So what we're going to do is write down. So I guess I'll start writing down the argument. So we're going to construct beta, which is going to have a decimal representation. Let me write it down here. So construct beta, which is going to be z1, z2, z3, z4, z5, ... by the following rules. So z1, so if a1 is not equal to 0, so if a1 is not equal to 0, let z1 be anything in the set from 1 through 9, excluding the digit a1. Okay, so so choose whichever your favorite number in that set is, and that is just going to so it would be an easier rule if whenever like a1 wasn't equal to 0, if we just set our first digit to 0, right? But we don't want to end up with a string of zeros for our number beta. So this very first one, if the first digit is not equal to 0, we're going to make it something not equal to 0. So just a little bit of a technical point there. And if, on the other hand, if a1 does equal to 0, then let z1 equal 1. Okay. Right, so we make z1, the first digit of beta, differ from the first digit of where g sends 1, right? And so that means that, so in particular here, so thus beta cannot equal g of 1, right? Okay, and then so once we've written down the first digit of our beta, then we move on to the second output of our function and the second digit of that second output. Right? So then if B2, so we're going to look at B2 now, if B2 is not equal to 0, then let Z2 equal 0, right? And if B2 does equal 0, let Z2 equal 1. Right? So again, in this case, thus beta can't be equal to G2. Right? Because our numbers have unique decimal representations, so if they disagree in even one digit of that decimal expansion, then they have to be different. And you just keep going on down the diagonal of this grid here. Right, so you think about this as a big, you sort of have horizontal and vertical movement in this grid. You go down the diagonal of it, and you just change every time. After the first digit, every time you see a 0, you put down 1 as your digit in that decimal place. If you see anything that's not equal to 0, you put down 0. Right? So then the next step would be if C2 is not equal to 0, C3 is not equal to 0, you let Z3 equal 0. If C3 does equal 0, you let Z3 be equal to 1. Right? So thus beta doesn't equal G of 3. Okay, and so you just continue in this way. And so clearly beta is, right, you're constructing it as this decimal, which is less than 1. It's not equal to 0, right? So it's not all zeros, because in the very first step here, we ensured that A1 was not equal to 0. And so clearly beta is in 0 to 1, right? So by construction, beta is less than 1, and beta is bigger than 0 because the first decimal is not equal to 0. Right? So the first decimal place is not equal to 0. But also clearly beta is in there, and beta does not equal G of n for every n, because they differ in the nth decimal place. They differ in the nth decimal place. And the decimal expansions are unique. And so one thing you can note about beta is that we're never going to write down an infinite string of 9s at the end, because we're always picking either 0 or 1. So if we did, if we had some other rule that wasn't as well defined, we might end up with an infinite string of 9s, and then it would turn out that the decimal expansion was in this way of writing down a unique decimal expansion was actually something kind of different than what we intended, and so then there might be problems. But we don't run into that trouble here because we're not writing down any 9s. So that's another slightly little technical point about this. But the main idea is just to change the nth decimal place of G of n and use that as to write down a beta. So that means thus beta is not in the range. It is not in the range of G. So G is not surjective. And so we've established that the reals have a cardinality larger than the cardinality of the natural numbers. And so there are different sizes of infinity in this sense. And now we'll follow that up with a definition. So basically any cardinality that's larger than the cardinality of the natural numbers, any infinite cardinality larger than the cardinality of the natural numbers is going to be called uncountable. So let's write down a definition. So a set A is called countably infinite. Countably infinite if the cardinality of A equals the cardinality of the natural numbers, right? If there's a bijection between that set and the natural numbers. A is countable if it's finite or countably infinite. And then if you have an infinite set which is not countably infinite, then that's called uncountable. So if A is infinite and the cardinality of A is not equal to the cardinality of the natural numbers, then A is called uncountable. Okay, so we just showed that the real numbers are an uncountable set. So R is uncountable. And the reason for the name countable is basically that you can put the elements of a countably infinite set in a list. So here's a convenient theorem. A set A is countably infinite if and only if its elements can be put in a list. Can be put in an infinite list. And the proof is simple. So any infinite list. So any infinite list, A1, A2, A3, A4, etc., just corresponds to a bijective function. So I guess I should say any list here of all of the elements of A, of all of the elements of A, corresponds to a bijective function, which just takes f at n and outputs a sub n, right? So this is a function from A to, or from the natural numbers to A. And so every time you have a list, that just means you're just writing down the elements of your set with subscripts, and then those subscripts, that tells you where to send your elements of the natural numbers. Okay, and if you have a function, right, then you can write down the list. So basically the correspondence is that f of n for any bijection, that just corresponds to your a sub n. Right, so that's how bijective functions correspond to lists like that. So here's a nice application of that. So question, if you have a set whose cardinality is less than or equal to the cardinality of the natural numbers, and let's say A is infinite, just to make it interesting. Finite is kind of not much to say, and A is infinite. Right. So basically, the question is it possible for there to be an infinite set which is strictly smaller? So is it possible that there's an infinity that's kind of smaller than the infinity of the natural numbers? And it turns out the answer is no. So the question is it possible that A is actually of strictly less cardinality than the natural numbers? And the answer is no. So basically, another way to frame the question is the cardinality of the natural numbers the smallest infinity? So is the cardinality of the natural numbers the smallest infinity? Or well, I guess this question is saying, is there a smaller infinity than that? So I should be more precise. So is there an infinity smaller than the cardinality of the natural numbers? And the answer is no. And the way you can see that is if the cardinality of A being less than the cardinality of the naturals, that exactly means that there's an injection. So there exists f from A to n, which is an injection. Right. So in other words, so in this case, that happens if and only if A is in bijective correspondence with a subset of n. So if and only if A is in bijective correspondence with the image of A, which is a subset of the natural numbers. And if A is infinite, then this f of A is going to be infinite as well. So this is an infinite subset of the natural numbers. And so the equivalent question basically then is just, is every infinite subset of the natural numbers have the same cardinality as the natural numbers itself? Or is it possible that there's an infinite subset of the naturals that has a strictly smaller cardinality than that of the natural numbers? And so again, the answer is no. And so here the precise statement is this theorem. So any infinite subset B contained in A of a countably infinite set A is also countably infinite. And so another way to say that is then that the cardinality of A equals the cardinality of B. And the proof is just that you can, since A is countably infinite, write the elements of A in a list. Elements of A in a list. And so you have A1, A2, A3, A4, etc. And then just delete all of the elements that are not in B. And what remains is an infinite list. Remains is an infinite list of the elements of B. So B is countably infinite. Okay, so the basic takeaway that you can remember is that the natural numbers have the smallest infinity possible. And so any infinity that might be smaller there'd have to be an injection from that set into the naturals. And so you would have this subset of the naturals, which would be the image of that original set by that injection, which had a smaller cardinality than n, but that's not possible by this theorem. Any infinite subset of n has the same cardinality as n. Okay, so the naturals represent the smallest possible infinity. So now you might wonder about ways of trying to create bigger infinities. So with countable sets. And so whether it's possible to combine countable sets together in various ways and make infinities that are bigger than countable. And basically it turns out that that you can't do that, at least for the simplest kind of constructions. So for example, here's an example of a theorem that if A and B are countably infinite, then A union B is countably infinite. Countably infinite. Okay, so combining a countable number of things with a countable number of things, you still have a countable number of things. And so the proof would be just write A and B in lists. So you have A1, A2, A3, dot, 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 and B1, B2, B3, dot, dot, dot. Then A union B, well, we can combine the lists. Let me say it this way. Then consider the list. We can just alternate between the list for A and the list for B and still get a list of everything. So then consider the list A1, B1, A2, B2, A3, B3. Right. So this contains everything in A union B. Possibly with duplicates, right? So A and B might have some intersections, so there might be some doubles in the list. So possibly with duplicates. And then if we delete the duplicates, then we'll still have an infinite list, right? So possibly with duplicates, just delete them. And we still have an infinite list. So I guess we can say like delete the duplicates from B, say, right? So the originals will always be from A. So we always have at least all of the elements of A in here. So definitely the list is still going to be infinite after we do this deleting. So just delete them and we still have an infinite list. So A union B is countable. Another way you can combine countable sets, which you might think would be bigger, is by taking their product. But it turns out that the product of countably infinite sets is still countably infinite. So the product A times B of countably infinite sets is still countably infinite. It is countably infinite. So proof. So what you do is create a grid by writing the list for A horizontally and the list for B vertically. Right, so you have the list for A, A1, A2, A3, A4, A5, etc. And then you have B1, B2, B3, B4, B5, etc. And then in the grid, every point in the product is represented by exactly one of these points here. And so there is everything with second coordinate and then dot, dot, dot. That's everything with second coordinate B1. And then this is everything with second coordinate B2, everything with second coordinate B3, everything with second coordinate B4, and everything with second coordinate B5. and then that goes on infinitely. And now to write them in a list, all you have to do is sort of write down all of these points sequentially. Right? So you can't do something like go this way, right? So start your list like this, because you never get to the end, right? So you never get to the end, you never get to the second row. So that is not going to work. And you can't go vertically, of course, but what you can do is just combine horizontal and vertical movement kind of alternatingly. So you can do something like, so follow this path, go, so like A1, B1 is your first thing on your list, then A2, B2, then A1, B2, and then you go, so basically you're sort of following, so the basic idea is to kind of follow, so I'll kind of draw the blue across. And so you start with the 1 point on that first blue diagonal there, and then you got 2 points in the second, 3 points in the third, and then 1, 2, 3, 4, right? And then 1, 2, 3, 4, 5, and you're just going to sort of pick them up in bigger and bigger triangles like this. So the first point here, and then the second and the third. So that's 1, 1, 2, and then 1, 2, 3, like this, and then 1, 2, 3, 4, and then down, and then 1, 2, 3, 4, 5. Right, so you just keep making these bigger and bigger triangles like this, moving out. Okay, so that's the scheme. So follow the arrows above to make the list for A cross B. Okay, so that's the proof that A times B is countably infinite if A and B are countably infinite. And then the corollary is that if A1 through AN are countably infinite, then so is A1 times ... AN. And the proof is just straightforward induction. I'm not even going to do it. I might have you, well, it would be a good exercise for you to do it. So I'll just assign it as an exercise for you to do at home. So straightforward induction. So basically the n equals 1 case is trivial, just because we have that by assumption, and then the n equals 2 case, we just did that, and then once you have that, then it's just a straightforward induction proof. So the only hard part is the n equal 2 case, which you need to use in the induction step. So as a combination of these, we can derive something which might seem a little bit surprising at first, which is that, so we know another natural infinite set of numbers, and that's the rational numbers. So you might wonder about the cardinality of the rational numbers. And the rational numbers might seem like a pretty big set. Like, they might seem like much more numerous than the natural numbers, right? Because like if you visualize things on the, so we know the natural numbers and the integers have the same cardinality. So let's think about the integers on the number line, right? So along like this, and that's going out in both directions. Now the rationals, well, we know that there's lots of rational numbers, in between any two any two integers here, like the halfway point, that's rational, and the halfway between the halfway points, those are rational. So these are each rational. The halfway point is rational. Halfway point, the halfway point, all the halfway points there, right? The 1/3 of the way between anything, right? So the thirds between everything, and then the fourths and the eighths, and so this interval gets sort of filled up with rationals very quick. And in fact, if you take if you let alpha be any real number whatsoever, then if you write alpha, so let's So if you write alpha in terms of a decimal representation, right? So you have some natural number, let's say m, and then you have a decimal after that, right? So you have a1, a2, a3, a4, dot, dot, dot. And let's say that alpha is not rational. So let's assume that alpha is not rational, right? Well, there's a sequence of rational numbers that get arbitrarily close to this alpha, right? So if you can consider the sequence of numbers like m, you can start with m, and then you got m, and then this is m plus a1 over 10, right? So that's rational, and then you have m plus a1 over 10 plus a2 over 100, that's rational, and m plus a1 over 10, a2 over 100, and a3 over 1,000. That's rational, right? Dot, dot, dot. And so and these are getting closer and closer, right? So these are approaching alpha as you write more and more digits. Right? So near any real number, you have infinitely many rational numbers that are getting, infinitely close to it. So no matter how close an interval you look at around alpha, you're always going to see infinitely many rational numbers there. Right, so it seems like Q seems dense in the real numbers in R in some sense, and so anywhere you are in R, you're always sort of crowded in by infinitely many rational numbers coming close to you. So it might seem like this is a very big infinity, and that you would naturally conjecture that it might be larger than the infinity of the natural numbers, but actually that is not the case. So it turns out that that Q is countably infinite, right? So this is equal to the cardinality of the natural numbers, so i.e. Q is countably infinite. And the proof is basically just from the definition of Q. Q is the elements of Q are defined by ratios of integers, right? So basically, what we're going to do is put a Q into correspondence with a subset of Z cross Z, more or less. And since we know Z times Z is a countably infinite set, any subset is going to be countably infinite by a previous theorem, and so Q will be countably infinite. So the details are that any R in the rationals can be uniquely written as R equals A over B, where A can be any integer, B is a natural number, and A and B have no common factors, and A, B have no common divisors. Right, so that is to say that if we write R as A over B in this way, so that is to say, if we write R equals A over B in this way, then f of R equals A comma B, right, where f here, this is a function from the rationals to a certain subset of Z cross N, where S equals, it's the set of AB in Z cross N such that A and B have no common divisors. Okay, so that is to say, if we write R as A over B in this way, then this function from Q to this set is a bijection. And so the uniqueness means that this function is injective, and of course any a and b in this set, when you look at a over b, that's a rational number. So that means that the function is surjective. And so this is a bijection, but z and n are countably infinite. Thus, so is z cross n, and S is a subset of this countably infinite set. So, and S is a subset, an infinite subset, is an infinite subset of this countably infinite set. So that means that S is countable, so the cardinality of S is equal to the cardinality of N, right? So thus, so we have the cardinality of Q, that's equal to the cardinality of this set S, because we created a bijection between them, and that's equal to the cardinality of N. So that implies that the cardinality of Q is equal to the cardinality of N. And that's it. So appearances can be quite deceiving. So even though this set sort of densely fills up the real numbers, in some sense it's still a long shot away from being as large as the real numbers themselves. So coming arbitrarily close to every real number is not the same as sort of being as numerous as the real numbers. So a natural question then arises of whether there are infinities that are larger than the infinity that comes from the cardinality of R. Right, so we know that so basically every infinite set that we've looked at other than R is just countable, right? So it's natural to wonder whether there's anything that might be bigger. Is the cardinality of R the biggest infinity possible? And the answer is no. So in other words, yes, there are infinities that are larger than the cardinality of the reals. So you might think that you should try to consider something simple like R cross R first. Maybe that has a cardinality larger than R itself. It turns out the answer is that cardinality is the same as the cardinality of R, and so the theorem that the product of countable infinities is still countable should convince you that probably there should be a bijection here as well. So basically you can't get bigger cardinalities just by taking products of sets, and I won't prove that precisely, but what we will do is look at the construction that works, which is that for any set A, the cardinality of A is less than the cardinality of the power set. Okay, that is, there's an injection from A to the power set of A, but there is no surjection from A to the power set of A. Okay, so clearly f of A equals the set containing A is an injection from F from A to power set of A. Okay, so we will show any G from A to the power set of A fails to be surjective. So let such a G be given. So what we have to do is construct some set X, some subset X of A, right? So subsets of A, that's the elements of the power set of A, right? So we're trying to construct some set X. So it's the set of X in A satisfying some mystery property, right? So we're going to try to figure out some property that's going to define a set that property, we want it to be such that this set x can't be in the image of this function f. So basically, somehow what we're going to expect here is that there's going to be some kind of property, some kind of, I don't know, like logical formula in terms of f. And so we want to figure out what this statement is here that defines that set x. And this argument is very much like Cantor's diagonalization argument. In some sense, it's a generalization of Cantor's diagonalization argument. Okay, so basically what we're going to do is to decide whether a particular x in A goes in this set or not. Okay, so the basic idea is, I guess I'm writing down here as scratch work first. So if you want to, so we need to decide, so trying to decide, so does x, little x, go in X or not? Okay, and so decide if little x goes in big X or not. So what you do is you look at f of x. And f of x is an element of the power set of A, right? So f of x is a subset of A. So the key thing is we don't want f of x to be equal to x, right? So in other words, I guess I could say it as we want f of x, this subset of A, to be not equal to the given set x, right? Or I'm sorry, not the given set x, the set we're trying to construct, capital X. And so the basic idea of how to make the set f of x and the set that we're constructing, capital X, not be equal is you're going to make them disagree about the membership of this little x that we're looking at, right? So we'll make them, so make f of x and capital X disagree about the inclusion of x. So that is, if the element x is in the subset f of x, then don't put little x in x. So then don't put little x in x. On the other hand, if x is not in its image subset f of x, then do include little x in x. So in other words, the criterion for our set x then, the things that go in x, they're the things in A such that they are not in their image sets. Right, so to decide if a little x is in big X, you look at the image set of x by, oh no, I did it again. I meant to be writing G when I've been writing F here. Okay, so I replaced all of the F's with G's. Okay, so to decide if an x is in A, you look at the set G of x, right? Our given function takes elements of A to subsets of A, right? So that subset that that corresponds to the input x, it might contain that element x or not. And if it doesn't contain, so if x is not contained in that subset G of x, then it goes into this set capital X that we're constructing. Okay, so leaving this down here for a second, so if we let G be given, define capital X to be the set of x in A, such that x is not in G of x. And then remember what we're trying to do, we're trying to show that this capital X is not G of something, right? And the reason is because x, the capital set capital X and all of the sets G of x, they disagree about the membership of x, right? So x is not in both of the sets, right? So they can't be the same set because they're going to disagree about the membership of little x. So for any for any x in A, there are two possibilities. So either x is in G of x, in which case x is not in capital X by definition, so that G of x cannot be equal to x. Right? So x, the capital X is not G of that little x, or x is not in G of x, in which case little x is in big X. So again, G of x, G of little x cannot be equal to big X, right? So thus, x is not equal to G of x for any x. And so G is not surjective. And so what this allows us to do here, so that's the whole proof. And then what we can do here is we can use this proposition to generate an infinite hierarchy of infinities. So you have the cardinality of the natural numbers. That's less than the cardinality of the power set of the natural numbers. Right? And that's less than the cardinality of the power set of the power set of the natural numbers. Right? And that's less than the cardinality of the power set of the power set of the power set of the natural numbers. And that just can go on forever there. Right? So there's infinitely many varieties of infinity. And in fact, this doesn't even get all of the various sizes of infinity. So there's other infinities that aren't even on this linear list here. And so there's even more infinities than you can kind of even imagine, even from this construction. And it's in fact, so that's a theorem. So it's a theorem that this cardinality here is the same as the cardinality of the real numbers. And you got to do a little bit of work to do that. So intuitively. So intuitively, again, the cardinality of R, that's equal to the cardinality of 0, 1, the interval from 0 to 1. And so we can replace this with 0, 1 if we want. And 0, 1, so you can represent things in here. Instead of in base 10, you can use base 2. So use base 2, and you get binary strings. So infinite binary strings. Infinite binary strings. And then subsets of the natural numbers. You can create infinite binary strings from this too, because if you have a subset of the natural numbers, then what you can do is for each, so for A, so if you're given some A, which is an element of the power set of n, then you can go through the natural numbers 1, 2, 3, 4, 5, etc., and you can create a binary string from this set A. So if 1 is not in A, you put down 0, and if 1 is in A, then you put down 1. So if you put down a 0 here, this would say that 1 is not in A. And if you put the 0 here again, 2, that would mean 2 is not in A. And then if 1 there, that would mean 3 is in A, and 4, maybe 0, so 4 not in A, etc. Right, so basically, roughly speaking, the reals between 0, 1 and the natural numbers correspond to infinite binary strings. So you kind of expect that they have the same cardinality. You have to worry about some details, and there's a theorem in that we don't have time to prove, which is called the Cantor. So Cantor-Schroeder-Bernstein theorem, which says that if you have an injection from A to B, and you have an injection from B to A, right, then in fact you have a bijection from A to B. Okay, so in other words, the intuitively plausible fact that if A is, if sort of the size of A is less than or equal to the size of B, and the size of B is less than or equal to the size of A, then they have the same size. But I mean, that sounds plausible when you say it that way, but you have to actually use the definitions that we've established to check that. And the argument is is really cool, but it's pretty involved to give a careful proof of that. And then it's even more work beyond that to use the Cantor-Schroeder-Bernstein theorem to show that R has the same cardinality as the power set of the naturals. So that's some details that are in the text that we're not going to have time for here, but I thought it'd be nice to tell you about them. And the one last thing I want to mention is what's called the continuum hypothesis. So this was a famous theorem, a famous open problem from the early part of the 20th century. So basically, Cantor wondered is there anything in between is there any infinities in between the infinity of the natural numbers and the infinity of the real numbers? And Cantor, by the way, he called this, so he had a special name for this. This is called Aleph naught. So that weird looking capital N, it's a Hebrew letter called Aleph, and so that was Cantor's notation for the cardinality of the natural numbers. And for this, so the cardinality of the power set, sometimes that's written as 2 to the cardinality. So this would be 2 to the cardinality of N, or 2 to the Aleph naught. And so Cantor wondered whether there was anything between Aleph naught and 2 to the Aleph naught. And so what Cantor thought, and that's what the continuum hypothesis is that the answer is no. So the continuum hypothesis is there is nothing between these two. So the first big contribution to the continuum hypothesis was by Gödel in 1940, who showed that it cannot be disproved by the Zermelo-Frankel plus choice axioms for set theory, sort of the generally accepted axioms of set theory. And the way he did this, so the way to think about this is that so he constructed a mathematical model of the axioms, so some model that satisfied all the axioms where the continuum hypothesis is true. So this means that the axioms don't imply the negation of the continuum hypothesis, right? But then the question remains, is the continuum hypothesis in this model only incidentally true, or is it true because of the axioms? Right, so it might just be that it just happens to be true in this particular model, and that it's not that it's implied by the axioms, it just sort of by happenstance is true. Then the breakthrough contribution was by Cohen in 63 and 64, who won a Fields Medal for his work, where he showed that the continuum hypothesis cannot be proved by the ZFC axioms. And he did this by constructing a model of the axioms in which the continuum hypothesis actually fails. So where there are sets in between the naturals and the reals with a different cardinality, whose cardinality is between that of the naturals and the reals. So all told, the continuum hypothesis is then independent of the axioms of set theory. It can't be said to hold or not to hold. It depends on what model of set theory you're working in. So the axioms are neither strong enough to say that it's true or not true. It's context dependent in some way, in some sense. All right, I think that is all we have time for.